In the previous subsection, we have learned the PD compensator. So PD compensator can improve the phase margin performance, but PD also decays the low-frequency loop gain, right? So in this subsection, we'll introduce another compensator, which is PI compensator. So PI compensator can improve the low-frequency gain and also can improve the regulation performance. So now let's look at what is PI compensation. So usually we also refer PI as the lag. Lag compensation. So the abbreviation PI refer to the proportional and integration. So PI compensator in mathematical essence, it is just a transfer function of GCS with such a format, GC infinity times 1 plus omega z over s, omega ls. So you can see that this part is just a inverted zero behavior, right? So this, usually we design this to be a low frequency inverted zero. So as I just mentioned that PI compensator is used to improve low frequency loop gain. And regulation. So we can plot its Boolean plot correspondingly based on this transfer function. So this is the frequency axis, and this is the compensator magnitude, right? And this is the phase. So inverted zero means that initially there is a minus 20 dB per decade slope. Until it hit this inverted zero frequency, we mark as FL, right? FL. Beyond this frequency, it becomes flat, right? Flat. So at high frequency, the level for this magnitude plot is equal to GC infinity. And for the phase plot, right, because this is an inverted zero, so initially there is a minus 90 degree, right, phase change. And starting from 1/10 of FL, there will be a rise. And beyond 10 times FL, it becomes flat. So level here will be 0 degree. So together, overall, this PI compensator will incur a 0 degree phase change, right? Phase change. So this means that if we place the FL at the low frequency, then for high frequency behavior, the PI compensator will not incur any phase change to the system. So we can still maintain the improved phase margin contributed by the PD compensator. Okay. Next, let's use an example to show you the function of the PI compensation. So usually the PI is extremely useful, right, for a scenario. So it's especially useful, simple, and useful for systems originally contain a single pole. So, for example, let's consider a original loop gain, right? Original loop gain with a single pole. The uncompensated, right, TU equals to TU0 divided by 1 plus S over omega P, right? So this is a single pole response for the uncompensated system, right? Now let's plot the uncompensated loop gain body plot. So x-axis is the frequency. Y-axis is the magnitude and phase. So for the uncompensated system, right, original, for such a system, we would have a body plot. So initially it's really low, mainly because TU0 is usually small, right, small. And at Fp, or we refer this omega 0 here to differentiate this with the PI compensator, right? So if we refer this F0, so for the phase, for the magnitude plot, so beyond F0, there will be minus 20 dB per decade change, right? And phase plot can also be plotted, right? So initially, 0 phase change, right? 0 degree. And starting from 1/10 of F0, there will begin to change, right? And ends at 10 times F0. So this is minus 90 degree. So the original body plot without compensation. So for such a body plot, you will see that there are some issues, right? First, the low frequency magnitude is really low, right? Previously, we learned that we want to achieve a high low frequency loop gain to suppress the input disturbance and also the load disturbance. But for this system, the low frequency gain is really low, which will make it insufficient to suppress the low frequency perturbations. And secondly, the crossover frequency is also low, right? We usually want to have a relatively higher crossover frequency. So how can we improve? Here comes the question. the answer is that we can use the PI compensator. So we add the PI compensator. So as I previously wrote, so PI compensator should have such a behavior. So essentially, it's just if we multiply compensator into the loop gain, right? Essentially, it's like we add those two Bode plots together, right? So we can see that we will first, at a low frequency range, we can lift the low frequency gain, right? So we would have a very effect, like, right? Suppose here is FL. FL is low frequency, right? We effectively lift the low frequency gain. So this is the compensated loop gain magnitude plot, right? So we can both lift the low frequency gain and push the crossover frequency to a higher value. Fc is moved to here. And on the other hand, if we look at the phase plot, right, basically it's like adding those two together. So initially there is a minus 90-degree phase change. Right? This is contributed by the PI compensator, as this phase plot indicates. But if the frequency is high enough, right, the PI compensator contributes 0 phase change. So it will overlap with original uncompensated system again. So this means that the phase margin is unaffected. Phase margin is unaffected, right? So this is compensated phase plot, okay? And one more thing is that we can calculate the value for this compensated crossover frequency. So basically, we look at the high frequency behavior. So at high frequency, so S is much larger than 1. So this can be approximately equals to S over omega 0, right? So this will be T magnitude can be calculated as TU0 times GC infinity divided by 1 is ignored, right? 1 is ignored. And this part is approximately equal to 1 at high frequency, because if denominator is much larger than numerator, this is 0. So here is the F over F0. So looking at this formula, we can calculate the crossover frequency, right? So Fc equals to approximately equal to TU0 GC infinity times F0. So that's the effect of the PI compensation. Okay, so in this section, we have introduced the design of the PI compensator. So we can see that PI compensator can actually effectively boost the low frequency gain and meanwhile keep the phase margin unchanged. And on the other hand, it can also push the crossover frequency to be high frequency to achieve a better dynamic response performance.